A very nice use of matrices is the use of transformations. In this lesson, we'll use matrices to determine the coordinates of translated or dilated figure and use matrix multiplication to find the coordinates of a reflected or rotated figure. How are transformations used in computer animation? Computer animation creates the illusion of motion by using a succession of computer-generated still images. Computer animation is used to create movie special effects and to simulate images that would be impossible to show otherwise. Complex geometric figures can be broken down into simple triangles and then moved into other parts of the screen. Points on a coordinate plane can be represented by matrices. The ordered pair xy can be represented by the column matrix xy. Likewise, polygons can be represented by placing all of the column matrices of the coordinates of the vertices into one matrix called a vertex matrix. Triangle ABC with vertices 3, 2, 4, -2, and 2, -1 can be represented by the following vertex matrix. So here we have all the x coordinates in the first row and the y coordinates are in the second row. Matrices can be used to perform transformations. Transformations are functions that map points of a preimage onto its image. If the image and preimage are congruent figures, the transformation is an isometry. One type of isometry is a translation. A translation occurs when a figure is moved from one location to another without changing its size, shape, or orientation. You can use matrix addition and a translation matrix to find the coordinates of the translated figure. Find the coordinates of the vertices of the image of quadrilateral ABCD with the following points. If it is moved 3 units to the right and 4 units up, then graph ABCD and its image. We write the vertex matrix for quadrilateral ABCD, so our x's are in the first row, and the y part of the ordered pair is in the second row. And they said we're going to move this 3 units to the right and 4 units up, so we're going to add 3 to the -5, so we've got -2, -2 plus 3 is 1, -1 plus 3 is 2, -3 plus 3 is 0, -1 plus 4 is 3, -1 plus 4 is still 3, -4 plus 4 is 0, and -5 plus 4 is -1. So the coordinates of the translated image are -2, 3, 1, 3, 2, 0, and 0, -1. And we can plot both sets of points, connect them, and we have both the image and preimage. Rectangle E prime, F prime, F, G prime, H prime is the result of translation of rectangle EFGH. A table of vertices of each rectangle is shown. Find the coordinates of F and G prime. Okay, I'm going to do G prime first because that's moving from left to right, the direction we're usually used to going. So if we look at H, for the x's, -2 plus something equals -5. So if I add 2 to both sides, I have x is -3. And for the y's, -2 plus something equals -4. I can add 2 to both sides, and so I find y is -2. So to find G prime, we're going to take 4 plus -3 for the x, and -2 plus -2 for the y, so we get 1, -4. Now for F, I know that some x, and my rule I know now is add -3, and I get 1. So if I add 3 to both sides, I know my x should be 4, and y plus -2 equals 0. So if I add 2 to both sides, I have y equals 2. So that means my ordered pair for F must be 4, 2. Okay, so translations weren't too scary. Let's move on to dilations. When a geometric figure is enlarged or reduced, the transformation is called a dilation. In a dilation, all linear measures of the image change in the same ratio. For example, if the length of each side of a figure doubles, then the perimeter doubles, and vice versa. You can use scalar multiplication to perform dilations. Triangle XYZ has vertices at 1, 2, 3, -1, and -1, -2. Dilate triangle XYZ so that its perimeter is twice the original perimeter. What are the coordinates of the vertices of triangle X prime, Y prime, Z prime? So all we're doing is doubling everything. So 2, 6, -2, 4, -2, -4. And we can plot points, graph the pre-image in its image, and you can see it has doubled in size. In addition to translations, reflections and rotations are also isometries. A reflection occurs when every point of a figure is mapped to a corresponding image across a line of symmetry using a reflection matrix. The matrices used for common reflections are shown below. Write these on a note card or in your notes someplace it's easy to find, because I don't have them memorized either. They're very similar to each other. For the x-axis, we've got 1, 0, 0, -1. For the y-axis, it's -1, 0, 0, 1. To reflect over the line y equals x, 0, 1, 1, 0. Find the coordinates of the vertices of the image of pentagon penta after reflection across the x-axis. So I look on my handy-dandy reference chart and I can see I want the reflection matrix 1, 0, 0, -1. And this is where we should have started when we were learning to multiply matrices, because when we go row by column, it doesn't get much easier than this. -3 plus 0. Oh, 0 plus -1. Guess what? Nothing's happening. I'm just copying them down. For the second row, though, I'm doing 0 times the x and -1 times the y. So guess what happens to the y values? Yup, it's the opposite of what we started with. And then once again, we can plot our points, connect the lines, and we have the pre-image and image after it has been reflected over the x-axis. A rotation occurs when a figure is moved around a center point, usually the origin. To determine the vertices of a figure's image by rotation, multiply its vertex matrix by a rotation matrix. Commonly used rotation matrices are summarized in the table. So 90 degrees, we've got 0, -1, 1, 0, 180, -1, 0, 0, -1, 270, 0, 1, -1, 0. Find the coordinates of the vertices of the image of triangle DEF after it's rotated 90 degrees. Look in my handy-dandy table. Counterclockwise about the origin. Remember, order does matter with matrix multiplication, so we need to write down our magical value that we found for the rotation matrix first, and then our vertex matrix, and then we get to multiply row by column. Let's see what's happening here. 0 times 4 is going to be 0. -1 times 3 is -3. So it looks like this time I'm doing the opposite of the y's where the x's used to be. And then we've got second row. So, 1 times 4 is 4 plus 0 times 3. So it looks like those are just going to be our old x values are now becoming our new y values. And once again, we can plot points, connect the dots, and graph our pre-image and image. And it has been rotated 90 degrees counterclockwise about the origin. Use matrix addition and a translation matrix to find the coordinates of a translated figure. Use scalar multiplication to perform dilations. To reflect a figure, multiply the vertex matrix on the left by a reflection matrix. To rotate a figure counterclockwise about the origin, multiply the vertex matrix on the left by a rotation matrix.